Welcome back. So now we're going to try finding the actual analytical solution. So the first step to do is, since we know that our differential equation dy by dx equals x cos y, this is a separable differential equation. What you can do is you can rewrite this. This will become secant y dy by dx equals x. And of course, if you integrate both sides with respect to x, we're going to end up with the integral of secant y dy equals x squared over 2 plus c. So in order to find this differential equation, we have to be able to find the integral of secant y. So let's just consider in general that we're trying to find the integral of secant x dx, and it gives us a hint here by writing the integral in terms of cos x and multiplying by cos x over cos x. So let's do that. We're going to get the integral of 1 over cos x, if we put it in terms of cos x, times cos x over cos x dx, and we're going to get, if we just expand this in now, the integral of cos x over cos squared x. And now we know that sine squared x plus cos squared x equals 1, so we can write this bottom part in terms of sine. We're going to get cos x over top of 1 minus sine squared x dx. So now from here, what you want to try doing is doing a u substitution. That's what I would do when I see this. So I would say let u equal sine x. So then du will be cos x dx. So if we put that in, we're going to get the integral of cos x over top of 1 minus u squared. And dx is going to be du over cos x, if you just rearrange this formula over here. So now we can cancel out some of the like terms. Cos x will cancel out. So we're going to be left with the integral of 1 over 1 minus u squared du. And the way you want to do this is use partial fractions. So I'll bring this over here. So you have the integral of 1 over 1 minus u times 1 plus u du. And so now what we're going to get here is, this will be the integral of some integer or some real number a over 1 minus u plus some real number b over 1 plus u with respect to u. And now you multiply both sides by 1 plus u. So this will be the integral of a times 1 plus u over, and then plus b times 1 minus u over top of 1 minus u times 1 plus u du. So now what we can do is we can re-expand, and we know that ultimately our top part will have to simplify down to 1. So we're going to end up getting a plus b is equal to 1, and a minus b equals 0. Because the term that has u is going to have to be equal to 0, so that's why you get this a minus b equals 0. So now if we solve for this, we're going to find that a equals 1 over 2, and that b equals 1 over 2. And so we're going to end up with the integral of 1 over 2 times 1 minus u plus the integral, or well, just plus the integral of 1 over 2 times 1 plus u du. So now this is fairly easy to integrate. We're going to get negative 1 over 2 ln of 1 minus u plus 1 over 2 ln of 1 plus u plus c. So now we can simplify this. This will be equal to 1/2 ln of 1 plus u over top of 1 minus u plus c. And the final step is just to return this u back in terms of x. And we know that u equals sine x, so we're going to be left with 1/2 ln of 1 plus sine x over top of 1 minus sine x plus c. So this down here is the solution to the integral of secant x. So now, part B says, hence solve the differential equation dy by dx equals x cos y. And we're given the hint to use identity arctanch x equals 1/2 ln of 1 plus x over 1 minus x. You might remember this from hyperbolic trig functions. This identity here is what will allow us to solve this differential equation. So, of course, we know that we're trying to find secant y times dy by dx equals x. So, of course, we want to find the integral of secant y dy by dx with respect to x equals the integral of x with respect to x. So now what we're going to get is the integral of secant y dy equals x squared over 2 plus c. Well, we know the integral of secant, that's what we got over here. So this will be 1 over 2 ln of 1 plus sine y over 1 minus sine y is equal to x squared over 2 plus c. And now we notice that this here is in the form of the hyperbolic tangent with x being sine y. So this is equal to arctanch of 1, or just of sine y is equal to x squared over 2 plus c. So now if we take the hyperbolic tangent of both sides, we can isolate for sine y. So we're going to get sine y equals tanh of x squared over 2 plus c. So then finally, our general solution is going to be y of x equals arc sine of tanh x squared over 2 plus c. Now we want to get the particular solution for the point y of 1 equals 0. So what this means is that we can substitute that coordinate in. So we know that we're going to get 0 equals arc sine of tanh of 1 over 2 plus c. So if we take sine to both sides, we're going to get 0 equals tanh of 1 over 2 plus c. And now you have to solve this, so you just put this in terms of exponentials. And for the sake of time, I'll just tell you that c, you should get c equals negative 1 over 2 when you solve for that. It's pretty easy to solve, though. So that's your answer for the c value. So therefore, the particular solution we're looking for is y of x equals arc sine of hyperbolic tangent of x squared minus 1 over 2. I just think this is a really cool solution, that somehow our differential equation, which has a cosine and our x here, somehow ends up having an inverse trigonometric function with a hyperbolic tangent function inside of it, with a quadratic inside of that. It's a really cool solution. So now, using that equation that we got here, we can find the exact solution to this point. So we know that y of 1.4 is going to be equal to arc sine of hyperbolic tangent of 1.4 squared minus 1 over 2. And so y of 1.4 is going to be equal to approximately 0.4625634262. This here is the actual solution to the differential equation y 1.4. So now the final step we want to do is we want to know which of our estimates in the beginning was more accurate, the one with the Euler's method or the one with the Taylor polynomial. So what we got to do is first I'll do the error in the Euler method. So error in Euler method. This is going to be percent error is going to be equal to 0.4499464095 minus 0.4625634262 divided by just that answer there, the exact one, 0.4625634262 times 100%. And so what you're going to get is that the percent error is going to be equal to 2.727629555%. That's for Euler's method, and that's pretty good. That's a pretty small deviation. So now let's check what our Taylor series estimate is. So if we now do the Taylor series one. We're going to find that percent error is going to equal 0.469333333. It's a full calculator display. Minus 0.46256344262 divided by the same thing again. Times 100%. And so when you put that in your calculator, you'll find that percent error is equal to 1.442451797% using the Taylor series. And so what we find is actually that third degree Taylor polynomial was more accurate than Euler's method with step size 0.1. And of course, you can get either one as accurate as you want by either decreasing the step size of Euler's method or increasing the number of terms in the Taylor series. But for this particular instance, our Taylor series approximation was a lot more accurate, within 1.5% pretty much. So therefore, our Taylor series approximation was more accurate. So I hope you found this differential equation challenge interesting. I certainly had a lot of fun making it, and I hope that it helps you with any differential equation practice that you may need for any test coming up.